The objective of this lesson is to bring together three separate parts of your physics course, and by comparing and contrasting them, as it were, you'd have a better understanding of what's going on overall. So the three things I want to talk about are gravitational fields, electric fields, and magnetic fields. And first, we must understand what a field is, I suppose. So you can think of it, there are three invisible force fields in your course in particular that we're talking about. So these are areas where an invisible force is felt for some reason, and we're going to go into those three reasons now. So the first one is a gravitational field, and that's caused by one or more masses. And so you've got two masses, and in theory, any two masses anywhere in the universe are going to exert some force on each other, and that's called gravity. Now, there's also electric fields. So again, any place you've got two charges, they will always have a force on each other, and that's an electric field. And finally, magnetic fields, again, north and south poles exert forces on each other, and we'll see about that later as well. So there are three diagrams here. So this is what's similar about them all, I suppose. Gravity, if you could see gravity, you might see something like this, invisible force field lines pulling stuff down to the earth, like this. If you could see the electric charge field lines, you'd see something like this again. You'd see, for example, in a plus charge and a minus charge, you might see these curved field lines here, where there's a force felt as well. There's a force felt by charges in there. And here, around the magnet, in a similar way, you see these magnetic field lines. And again, that's an area where there's a force felt. So these are invisible field lines in all three cases, and there's always a force felt in that area where those field lines are. So that's what they all have in common, first of all. Now, let's see what's different about them, I suppose. Let's look at them all individually. And first, we're going to look at gravitational fields. So what's happening here is there is a universal law called Newton's universal law of gravitation. And that determines that whenever there are two masses anywhere in the universe, there's a force between them. And the force is given by this equation, G m1. So G is the universal constant. Mass of the first object by mass of the second object over r squared. So that's the force that determines the field lines, or the force along the field lines in a gravity field. And you can see the equation here. So again, that's Newton's universal law of gravitation. Now, the direction of the force, is basically, it's always attractive, first of all, in a gravity field. It's always an attractive force between the two objects. They never repel. So the force is felt along those two lines there, and you can see the arrows pointing along the direction of the force. Now, we have to mention at this stage as well, it's what's called an inverse square law, because the force is proportional to 1 over the distance squared. So what that means is if you halve the distance, 1 over 2, so 2 squared, so force is multiplied by 4, for example. So half means 2 squared gives you a force of 4. If you have a third of the distance, 3 squared is 9, so the force is 9 times stronger, and so on. So that's an inverse square law. And we'll come across that again as well. So there's just a diagram showing the inverse square law. Now we go on to the concepts of potential and kinetic energy, and because of these force fields, if you lift something against this field, so there's the Earth, and you lift some object up against the field, so the field is always pulling down, you are now giving it potential to fall back down again. If you take your hand away, the Earth's gravitational field will pull that object back down. So the higher you lift something, the more potential you are giving it to fall back again under the Earth's gravitational field. And we can work out the energy involved here, the energy it builds up by lifting it. So work is force by distance, and the force is, in the case of this, it's the weight of the object pulling it down, which is mass by acceleration, and acceleration is gravity, so it's mg. So putting all that together, you just get an equation for work is force by distance, which is weight by the height. So the work that will be done, or the work, if you like, work or energy that it builds up, being lifted through a height h, can now be given by weight by distance, which is basically mg by h. So we have a formula for the potential you build up by lifting something against the Earth's gravitational field. So that's potential energy. And now if you let it go again, if something has been lifted through a height h and you leave it fall again, it's been pulled down by the Earth's gravity, so it gains kinetic energy. So that potential is converted to kinetic. So the loss in mgh, or potential, is the gain in kinetic, and the formula for that is half mv squared. Now on to electric fields. So there's a very similar type law for, it's also an inverse square law for the attraction between charges in an electric field. So these are two charged objects, Q1 and Q2. So the force between them is, again, it's like the masses for gravitational law, but instead of mass 1 by mass 2, it's now charge 1 by charge 2. And of course, the distance part is the same as gravitational law. It's an inverse square law. It's proportional to 1 over the distance squared, the distance between the charges. So that part is similar to Newton's law, Newton's gravitational law. And again, so there's now a field, because of these two charges and this force between them, there's now an invisible field around here where there's a force felt. Now that field, of course, only affects other charges. It doesn't affect other objects. It's an electric field this time, so it doesn't affect every object like the gravitational field does. So that's one difference, I suppose. So that's one difference between the two fields at this stage. So this is called an electrostatic force. And so the law here is called Coulomb's law, the law that decides the attraction between them. Now, one difference here as well is and this is often asked in the Leaving Cert exam, differences and similarities between the laws. This is attractive or repulsive. If these are two like charges, if that's a plus charge and that's a plus charge, they will repel. If they're unlike, they will attract. Whereas in the case of gravity, it's always attractive. It's always an attractive force. That's one big difference here. These can attract or repel charges, whereas in gravity, masses can only attract. And so there's the formula, and there are the field lines there, as you can see. Now, how do you decide in an exam which way to draw these field lines? I think it's always useful to think of this phrase here: parachute in a plus charge. So PP, parachute, and plus are positive. If you imagine parachuting in a plus charge here, for example, what would happen to it? Well, it's repelled by another plus, so it's pushed along this line, and it's pulled by a minus. So that's why the arrow goes in that direction. Always think, if you parachute in a plus charge, what would happen to that charge? The same out here. If I parachute in a plus, it's pushed out along here. If I parachute in a plus over here, it's pulled towards here, because that's the opposite charge, so it's attractive. Over here, what happens? These are two pluses. If I parachute in a plus charge here, he's pushed out, he's repelled. He's also repelled from this side by this guy, so he's nowhere to go, so he just goes out into the distance there. And that's why those two, when they come together, they spread out like that. So always think, as I said, parachute in a plus charge. Now, we have a similar concept to potential energy that we came across earlier for gravitational fields. It was mgh. Whereas now we have a similar idea of potential. You can build up charge in a certain area, and that's just like gravity in some ways, because if we just go to the equations here, there's now a concept called voltage. And if you have basically, first of all, the definition of voltage is the work done per charge. When the charge is moving in an electric field, it's the work done per charge, per Coulomb. Now, if you rearrange that formula, work or energy, same thing, is now charge by voltage. So we have a formula for the energy. And this is the equivalent of your potential energy in gravity, really. So it's the energy due to an electric field. So if you take a charge, if you come up here, and if the charge, this is okay, this is gravity down here. This is gravity. This is electric charges up here. So we all know a mass falls, it's pulled by gravity down a hill, for example. But it's the same concept here. Here's a charge pulled by a minus here. So there's a massive pull by the minus here. So that's like falling in an electric field. That's the equivalent idea. And when something falls in a gravitational field down here, we can work out the energy. The potential to fall is mgh. The same here, the potential to fall from here to here is gravity, is the electrical potential, which is W, which is charge by voltage, where voltage is the voltage between here and here. So now we have, again, the same concept as we had for gravity. The energy lost in a gravity field is the kinetic energy gained. Same here, the potential energy lost here. QV is the equivalent of the kinetic energy gained, half mv squared. So that's QV is a half mv squared, and if it's one electron, which it very often is in your physics course, the charge on an electron is 1.6 by 10 to the minus 19. So you can measure that. Q becomes E, so the formula becomes EV is a half mv squared. So for example, in the cathode ray tube or the X-ray tube questions, you might often have to use this formula where the electron is going across an electric field, so it's losing electrical potential EV, and it's gaining electrical kinetic energy, which is a half mv squared. Also, this value of E might be more in the tables. You better look it up as well. It's slightly more accurate than that in the tables. 1.6, there are more decimal places. There's also a concept called electric field strength on your course, and that brings us back to Coulomb's law for a second. If you look at Coulomb's law, there's one disadvantage, I suppose. There's a formula for force, but that's the force between two charges. It doesn't tell you, the breakdown of what each charge contributes, I suppose. So that's the problem with that. It's just generally for two charges only. If you're interested in one area of charge, one point of charge in a field, and you want to find out the effect due to that one charge, that's where electric field strength comes in. And it's the equivalent, I always find, to explain the concept, it's like two men having a tug of war. And the guy putting to the left is winning, for example. That doesn't tell you anything about how strong he is, because it depends on the guy on the right as well. So it's the same problem. How do you judge each man's actual strength if you're going to use a tug of war to judge it? And I suppose the fairest way would be to get one fella who's, say, we call him Joe for the sake of argument, if they all pull against the same guy every time, and then we have maybe a better idea who's the strongest. If they're all pulling, if it's a fair test, basically, they're all pulling against the same guy. And it's the same thing in this. What we decide to do to find out how strong an individual charge is, I suppose, or what he contributes to the force, we'll say there's Q1 and Q2. We'll make charge 2 1 always, make him 1 Coulomb. So you're putting against the same guy every time. And when you do that, you're now getting the field strength, as it's called, due to Q1. And it's as simple as that. You're now getting a more realistic number to measure what Q1 is contributing. And everything else is the same. That's the same thing, by the way, as taking Coulomb's law and dividing by Q2, because in Coulomb's law it's Q1 by Q2. So if you divide by Q2, the Q2 is gone, and you just get the same result. So that's the equation for what's called electric field strength. And so that measures the strength due to a particular charge in a field. And last but not least, magnetic fields. So it turns out there's also an equation to describe those, just like there's Coulomb's law for electric fields, and there is Newton's law for gravitational fields. But actually, the magnetic field equation is not on our course, so we don't have to worry about that. And we just have to worry basically about I suppose, the physical aspect of it. And again, you would need to know how to draw the field lines with the correct arrows. So what's happening here again is, think of, as I said the last time, parachuting in a plus charge for an electric field. We'll parachute in a north pole here. If you parachute in a north pole, if you could isolate a north pole and parachute it in, what will happen to it? So a north pole will be pushed by this north pole here and pulled by a south pole, which is the opposite. So again, just like charges, so there's a similarity here. Like poles repel, unlike poles attract. So a north pole will be pushed from here and pulled along here towards the south pole, and that's why those field lines have the arrow going that direction.